Hello my dear students, welcome to Fluid Mechanics lecture series. I am your Suma Miss. My channel name is also Suma Miss. You can watch my videos on my channel. If you found useful, please don't forget to like, share, comment. Your comments are highly valuable to me. The topic for today's discussion is action of fluid pressure on submerged curved surface. In many engineering applications, it is necessary to know the magnitude, direction and location of resultant hydrostatic force exerted by liquid in static condition on submerged curved surface. For example, the pressure force acting on curved surface of ship or submarine which are under rest in water, or curved gate Forrest Lewis. Now let us discuss the pressure force that is acting on the curved corner AB. So it is given that OA and OB that is equal to 0.5 meter. The pressure force P that is resolved into PH and PV. The horizontal component of resultant hydrostatic force may be obtained by projecting this curved surface AB upon a vertical plane. So this PQ that is the projected area. So it is given that length that is equal to 1. So OA equal to OB equal to 0.5. So that is equal to PQ and length is given as 1 meter. So area of this vertical plane that is equal to PQ into 1. So that is equal to 0.5 meter square. And the center of gravity of this vertical plane with respect to free surface that is equal to 0.5 plus 0.5 by 2 that is equal to 0.75. Now the horizontal component of resultant hydrostatic force that is equal to ρg into A into h bar can be calculated as 3.678 kilonewton. Now comes to the vertical component of resultant hydrostatic force. So that is equal to this weight of this liquid prism that is acting vertically over this curved surface AB. So that is equal to the entire area multiplied with the length 1. So that will give you the volume multiplied with the ρg. So OA into 0.5 represents the area of CAOD and pi by 4 into OA square represents the area of the quarter of the circle because OA represents the radius. So this is the total area multiplied with 1 will give you the volume of this water available here into ρg will give you the weight. So PV equal to 4.378 kilonewton. Now how will you calculate resultant? That is equal to root of pH square plus PV square which is equal to 5.72 kilonewton. And the line of action of this resultant hydrostatic force that is equal to tan inverse of PV by pH equal to 50 degree with respect to the horizontal. So this is similar to the case of water in a cylindrical storage tank or petroleum tank, etc. In this way we can calculate the resultant hydrostatic force. Next problem what we are going to discuss is the pressure force that is acting on the curved surface of the dam. So BC represents the curved surface of the dam and this dam is having the height 8 meter. And the surface is shaped according to the relation y equal to x square by 2. So the profile of this BC that is given as y equal to x square by 2. So as we discussed earlier, horizontal component of hydrostatic force that is equal to vertical projection of this curved surface upon a vertical plane. So it is having height equal to 8 meter and we are considering unit length. So area equal to 8 into 1 which is acting at a distance of 8 by 2 from the free surface. So horizontal component of P equal to ρg into A into h bar equal to ρg into area into h bar equal to 313.92 kilonewton. Now how will you calculate the vertical component? Vertical component means the weight of the water that is available here. So for which we need the calculation of area ABC. We can consider a small strip here with a thickness dy. So area dA equal to x into dy. So x equal to root 2 into y raised to half. So if you are substituting here, dA equal to root 2 y raised to half dy. Since the dam is having height 8 meter, total area equal to integral of 0 to 8 dA. So in order to calculate the vertical component of resultant hydrostatic force, we have to calculate the weight of the water enclosed by ABC. So that can be obtained as vertical component of P equal to weight of the water above BC, that is equal to rho g into area ABC into 1. 1 stands for unit length of the dam. So that is equal to rho g into integral of 0 to 8 dA into 1. So this stands for the volume of the water that is available multiplied with the specific weight will give you the weight of the water that is acting over this curved surface BC. So if you are integrating this between the limits 0 to 8, then vertical component of P obtained as 209.276 kilonewton. Next step is to calculate the resultant hydrostatic force, that is equal to 377.28 kilonewton, and the point of action of resultant hydrostatic force, that is equal to tan inverse of PV by PH, that is equal to 33.69 degree. That is the angle made by the resultant with respect to horizontal. This calculation we can use to calculate the resultant hydrostatic force and the point of action of the hydrostatic force on the surface of the dam. Next is to calculate the pressure force and the line of action of the pressure force acting on a sector gate. So BA is the sector gate which is supported by a structure frame hinged at the point O. OA equal to OB, that is given as 5 meter, that is equal to radius, and the enclosed angle phi, that is equal to 60 degree. So resultant hydrostatic force having two components, pH can be calculated by projecting this AB upon a vertical plane. So this is the projected plane. So horizontal component of P on the curved surface BA, that is equal to pressure force on the projected area on a vertical plane BD. So that is equal to rho g into A into H bar. So BD equal to AE equal to OA sin 60, that is equal to 4.33 meter. So BD equal to 4.33 meter and the length is given as 10 meter. So area A equal to 4.33 multiplied with the 10 and H bar is BD by 2 or it is equal to 4.33 by 2. So horizontal component of P can be calculated as, so pH equal to rho g H bar equal to 9810 into area multiplied with H bar equal to 919.63 kilonewton. So here we have to calculate the line of action of horizontal force. So since it is a vertical plane which is immersed under water, the pressure may vary from point to point and pressure increases when we move down. So horizontal component of pressure force, that is not acting through the center of gravity, but it is acting through a point that is called the center of pressure. How to calculate the center of pressure for a vertical plane that is immersed in water is given in this video, so you can refer this. HP equal to, so line of action of this horizontal component can be calculated as Ig by AH bar plus H bar. So this plane is having length 10 and depth 4.33. So Ig equal to 10 into 4.33 cube by 12 as the equation BDQ by 12, that is equal to 67.65 meters raised to 4. So if you are calculating H bar equal to 4.33 by 2, so HB equal to 2.886 meter. So you can watch this video that will give you the procedure of how to calculate the center of pressure for a vertical plane. So next step is to calculate the vertical component of the resultant hydrostatic force. So that is equal to the weight of the water that is enclosed in ABDA. So this weight of the water that is acting vertically down over the curved face BA. So how will you calculate this area? Because length is given as 10 meter. So this area, that is ABDA, is calculated by deducting the sector area from the total area that is available. So vertical component of P, that is equal to weight of the water supported by BA, that is equal to rho g into area ABDA multiplied with the length. So area ABDA equal to area AEBD plus the area OAE minus sector area, that is OAB. So area ABDA equal to, this angle is given as 60 degree and OA is given as 5 meter. So 5 cos 60 will give you OE. So that is equal to 2.5 and OE equal to 2.5, then total distance OB is 5. So OE equal to EB, that is equal to 2.5. Area AEBD equal to 4.33 multiplied with 2.5, that is given as 10.825 Then area of the triangle equal to half BH. So half into 2.5 into 4.33. So that is given as 5.4125. Then this is 60 degree, this angle. So area OAB, that is equal to total area of the circle by 6. So that means pi r square by 6, that is given as 13.09. So from this calculation, the area ABDA, that is obtained as 3.15 meter square. So if you are substituting this area, then vertical component of P is obtained as ρg multiplied with the area into length. This will give you the volume. So vertical component of P equal to 309.015 kilonewton, and resultant hydrostatic force, that is equal to root of pH square plus PV square, that is equal to 970.16 kilonewton, and it is acting through an angle 18.57 degree with respect to horizontal. So in this problem, we calculated the resultant hydrostatic force and the point of action of the resultant hydrostatic force. The next portion is line of action of horizontal and vertical component. So line of action of horizontal components we already determined, that is S 2.886 meter. So the next step is to calculate the line of action of vertical component, that is line of action of PV. So line of action of this horizontal component, that is equal to 2.886 meter. And now vertical component of resultant hydrostatic force, that is equal to the weight of the water that is enclosed in ABDA. So let us consider G is the center of gravity of this area, that is area ABDA, which is at a distance of x from the hinge. Similarly, if you are considering the area of this rectangle, that is DAEB, its center of gravity, that is indicated by G1. Now the area of the sector, that is OAB, its center of gravity is indicated by G3, and area of this triangle OAE, here the center of gravity is marked as G2. So in order to find out the line of action of the vertical component of resultant hydrostatic force, we have to consider the moment of these four areas about this point O, that is about the hinge. Now theta, that is angle, that is equal to 5 by 2. So if you are dropping the vertical to the line of hinge, then G1 dash, that is the point vertically below G1, similarly G3 dash and G2 dash. In order to take the moment of these four areas about this hinge O, we have to get the value of G1 dash O and G3 dash O and G2 dash O. G1 is the centroid of DAEB and G1 dash is vertical. So this distance is 2.5 and this distance is also 2.5. So the position of G1 dash is at a distance of 2.5 plus 2.5 by 2, that is 3.75 from this hinge O. Similarly, G2, that is centroid of OAE. OAE means this triangle OAE, and G2 dash is vertical. So this distance is 2.5. So the position of G2 dash is at a distance of, it is equal to 2/3 of 2.5. So that is equal to 1.67. Now comes to the sector. So this is a sector. So G3 dash O we have to calculate. So what is this G3O? Centroid of sector, that is equal to 2r sin theta by 3 theta, where theta is equal to 5 by 2. Phi is given as 60 degree, so 5 by 2 equal to 30. That is the position of the centroid of the sector, that is equal to 2r sin theta by 3 theta, where r is the radius that is given to you, and theta, that is equal to 30. So that will give you OG3. So G3 dash O equal to G3O into cos 30. G3O, that is equal to 3.183 into cos 30 will give you the value of G3 dash O. So by taking the moment of these four areas about O, moment of this area DAEB about O plus the moment of this triangle OAE about O, that is equal to, so the moment of the area of the sector about this O plus moment of the area, that is ABDA about O. So if you are substituting, then it is equal to area ABDA into X plus area of the sector into G3-O, that is equal to area AEBD into G1-O plus area OAE, that is area of the triangle, into G2-O. All these areas are available, so we can substitute, and G3-O, G1-O and G2-O, that is also available. So if you are substituting, the line of action of this force PV passing through G, that is centroid of BDA, that is equal to 4.287 meter. That means X equal to 4.287 meter. So from this problem, we are able to calculate the line of action of horizontal force component and vertical force component and the line of action of the resultant force. So based on the calculation, we can fix the position of the hinge. Next type of problems we have to face is the curved surface which is coinciding with the level of the liquid. So here the curved surface is AB that retains water. So vertical section of the surface is a quarter of the circle having radius 1.5 meter, and this surface is 2.5 meter long. So as we discussed earlier, horizontal component of the pressure force, which is calculated by projecting this curved surface over a vertical plane and multiplying the area of the plane by the pressure through the centroid of this area. So here BB dash, that is the projected area. So BB dash, that is equal to the radius. So pH can be calculated as ρg multiplied with the length into 1.5. So that is this side. So 2.5 into 1.5 will give you the area into 1.5 by 2. So this is h bar, that is equal to 27.59 kilonewton. The vertical component, that is equal to the weight of the water that is available. So here there is an imaginary weight of water that is available enclosed in AB dash B. So which is equal to area of OAB dash B minus area OAB. So in the horizontal component of pressure force that is acting in the horizontal direction, whereas here you can see that vertical component of the resultant hydrostatic force acting upward. So when we are resolving the forces into horizontal and vertical component, horizontal force is same as we discussed earlier, but vertical force that is acting upward. So vertical component of the resultant hydrostatic force, that is equal to the weight of the water that is enclosed within A B dash B, which is equal to ρg into the area A B dash B O minus area of the quarter of the circle, that is equal to 11.843 kilonewton. So which is acting upward. So resultant hydrostatic force equal to root of pH square plus PV square, and the line of action of this resultant hydrostatic force equal to 23.24 degree. But when the problem is coming like this, that means this is a curved surface, but it is not coinciding with the water surface. The water is available up to this height. So horizontal component, that is same as we discussed earlier, that is the pressure force which is acting on the vertical projection of this curved surface AB, that is the pressure force which is acting on this plane BB dash, which is equal to area of this plane multiplied with the pressure that is passing through the centroid of this area. Whereas vertical component, that is acting upward, which is equal to weight of the water column that is enclosed by A B dash B plus the water is available up to this height. So we have to consider the weight of the water that is available, that is enclosed within this PQ B dash A. So PV, that is equal to the weight of the water that is enclosed within PQ B dash BA, but it is acting in the upward direction. Now the session comes to an end. So in this class we have discussed different type of problems generally we can see in the field. The calculation of resultant hydrostatic force and the point of application of resultant hydrostatic force is very much useful in many engineering applications. For the time being, it is enough. Thank you.